Okay, so thanks a lot for very kind words, Tias. I'm just going to put this chair here. Yeah, and thanks a lot for organizing and for inviting me. I'm very excited to be here today. And well, maybe I don't need to talk anymore because Tia's already mentioned it all. But I will go also over yeah, basically the past few years of my life, you could say, some of the research I did, and also into these challenges I mentioned. And I think they all sort of line up to what is my ultimate goal to encourage actually people like you to work more on like machine learning for optimization problems and specifically vehicle routing problems, which has my personal interest. And so maybe first, very quickly, a bit of introduction about me. So my name is Wouter. I have a background actually in, well, I studied business analytics, but econometrics and operations research. I did a master's, and then a few years later, I worked for a few years at Ortec, and then I felt like, hey, we should be doing more with machine learning, right? We were really doing a lot of operations research and heuristics, but this machine learning field was picking up traction. So I proposed to do a PhD on this topic of machine learning for optimization problems, which I did at the University of Amsterdam as part of my employment at Ortec. And so with that, I've been over 9 years already at Ortec in total. And like I mentioned, I did my PhD at the Amsterdam Machine Learning Lab. And during my PhD, I also was intern at Google DeepMind. So I've been really, let's say, close to where it happens in the field of machine learning, but also a very strong background in operations research. And well, I think the best of both worlds is what in the end can bring the best to our world, let's say. So that's, well, I think that's also why this summer school is here, which I really appreciate. But I always like to start my talks with a small example, which is about the traveling scientist. So all of you are scientists, I guess. Some of you are from here, but many traveled here. And I think this example is especially relevant. Tonight you will have the poster session. We spent quite some time during the speaker dinner actually discussing the logistics of this. And by the way, for some of you, if you have already seen some of my talks, I reused some slides, but there will be new material as well. Yeah, that's good to know in terms of expectations. But let's say tonight there's this poster session, and you already know actually which posters there are, where they are located, right? And you want to make sure that you don't spend too much time walking around, because you need to spend your time talking to other people, right? And learning about all this interesting work we are all doing. So this is what I call the traveling scientist problem, right? So if we start at the coffee corner, if we need to visit some places, how do we do that the most efficient way, get back to where we started? And as you may know, this is a very difficult problem, right? Which means that we have very little hopes of finding an algorithm that is able to actually solve any problem instance of this to optimality. So that's my next slide, actually. But it means that if we want to hope to find, let's say, an optimal solution for any given problem instance that we can possibly imagine, this is quite unlikely to happen. At least I think that's the common belief. But of course, from a practical perspective, right, I work at an optimization company, we do route optimization for our customers. That is actually not what we want, right? We want to find good or like acceptable or like as good as possible solutions for, I think, very nice problem instances with like specific properties which we see in the real world. And that is actually much more doable, right? And for that reason, we actually have a lot of heuristics, which I like to explain sometimes as rules of thumb, right? So if I talk about vehicle routing, heuristic, for example, then if I'm going to drive around, I'm not going to drive around randomly, but probably the next location I visit should be quite nearby, right? So that's a very simple heuristic. And now traditionally, I think, well, there's of course like exact methods in operations research, but people also design a lot of heuristics, and this is quite challenging, right? At least it's a lot of work to make this type of heuristics, and that is a bit similar to how in the past, let's say people in machine learning, for example, for computer vision, would do like feature engineering, like how do we recognize images? And so with that, we see now for a few years that we have a trend where we can actually replace that feature engineering or heuristic design, and we can use deep learning approaches to sort of do that, what we call end-to-end. And I think, yeah, this end-to-end approach is really nice, also explained yesterday by Elias quite a lot. That we can really just use learning to do what maybe classically we used to do by hand. And so, from a bit of an historical perspective, this started a few years ago, and there was this first idea by some people, which I think was very nice. They said, like, hey, if we can use machine learning, for example, to do translation, right? If we can translate some sentence into another language, then maybe if we have an optimization problem, we can sort of use the same methodology to just, you know, instead of predicting a translation, just predict a solution to an optimization problem. So if we have a closer look at that, it means that, for example, if I have a sentence, right, which I want to translate, I can use some machine learning model, and it's gonna like spit out a translation for that sentence. I think by now, none of you is surprised that this is possible using machine learning. But what these people said, I think this was like 2017, 2000, no, maybe 2015, just before I started my PhD. So okay, let's say traveling scientist problem. We have like a set of locations which we can just express as coordinates, right? And basically the goal is to put them in a different order, which is like the optimal order in which I should visit them. So that's like a sequence prediction problem, you could say. And you can model this in the same way as how you would model a translation problem, which is basically predict a sequence of words, which is the translation for this input sentence. And now, typically, right, and this is a challenge, if you would predict, let's say, words from a language, you always have like, the language just has a given vocabulary of words, let's say. So you predict outputs from a fixed vocabulary, and this is a bit different if you want to predict like a sequence of locations that you want to optimize over. Then basically your outputs, they refer back to your inputs, right? So you try to predict in which order should I put my inputs. And so for this, you need a different type of neural network architecture, actually. And this was developed, like I said, in 2015 with a very influential, I would say, pointer networks paper. And so basically what that comes down to then is that if we have this problem instance, right, this DSP problem that we want to optimize, then we're just going to give it to a neural network. So we assume now we have a trained neural network, and this neural network, it's going to make predictions, and it's going to predict, like given the starting location, like where should I go next. And this can be a probability distribution, right? Neural networks always predict a probability distribution. You never get like any certainty, let's say. But you can sample from this, or you can just pick the location with the highest probability. You can move there, and then we get sort of like this partial solution. We can feed that actually back into our neural network and then make the prediction for the next step. So where should we go next? And this we can then repeat. And by repeating this again, so you put this back into your neural network, makes the next prediction, we can all see that we can make a complete tour, right? And it's quite easy in this case to guarantee feasibility, because you can just, let's say, restrict the model from predicting locations that it already visited. And this way you can make sure that you get like a feasible DSP solution. And this is what we call an autoregressive model, actually. And this is also how all these like language models like ChatGPT nowadays work. So they predict like one word, then they take that as input to predict the next word. And I think a lot of people have done like, followed up on this and done like similar approaches to basically do construction algorithms for all types of optimization problems, where you can just predict part of the solution, you can take that as input to predict, let's say, the next part of the solution. And that's, let's say, the view from a prediction perspective. But you can also consider this in machine learning terminology. So with that, we can say that we have an instance, which we call S, which is then, in this case, a set of X and Y coordinates, right? These are the locations that we want to visit. And what we're trying to predict is a solution, right? Which is a permutation. That's why we use pi. As of the input coordinates, and it has a certain length, right, that we can compute. And then in between we have what we call the model, and the model basically models the probability distribution of the next node given the partial tour or partial solution that we have already constructed. And in this terminology, all these steps, let's say where we apply the model and we pick the next location to visit, they are sampling steps, right? We're sampling according to a probability distribution, like where do we go next, and we can do that one by one. But of course, by sampling all the steps one by one, we get like a distribution over the complete space of possible tours that exist. And with that, from that perspective, this is actually a randomized algorithm, you could say. It randomly constructs a tour. For each tour, we can compute the length or the cost or whatever, and that means we have a randomized algorithm which has a certain expected cost, right? And now the clue is that this expected cost, so that basically that's a proxy for like the quality of your algorithm, that depends on the parameters of your neural network, right? Because your neural network is going to make these predictions of where to go next. Your neural network has a set of parameters, and you know, the parameters of the neural network, they determine whether you get good tours or whether you get bad tours. So the question is, how can we optimize these parameters such that we get shortest possible tours if we're going to sample according to these predictions from the neural network? And then there was this very nice paper which proposed that we can actually optimize this, which probably shouldn't surprise you, using reinforcement learning. Right, and now I don't want to insult anyone, but I think it's always good to do a quick recap, or, well, possibly too simple explanation of what is reinforcement learning. So the way I'd like to explain it or think about reinforcement learning is basically you just try something, right? So in this case, it means you just sample a solution, you sample the tour, then you observe the result. If it's good, you do it more often. If it's bad, you do it less often. In my perspective, this is the essence of reinforcement learning. And what does that mean in our case? Like I said, just doing something that is creating a solution, right? Creating a tour, and then observing the result. It's computing the length for that tour, right? Just computing the objective function in more generality. And now, of course, if that's a good solution, you're just going to change your parameters, right? You can do backpropagation and gradient descent. You can make it actually more likely that you get this solution, whereas if it's a bad solution, you would just change your parameters such that it becomes less likely that you would get this solution for the same problem instance. However, the question is, if I have a tour of length, let's say 7.43, is that a good solution or not? And in order to be able to answer that question, we need something to compare against, right? So in reinforcement learning, this is what we call a baseline. And what we proposed actually a few years ago is to just use an earlier version of the model. So you just create another solution. If you create then a second solution, if it's better, then it's good. If it's worse, then it's not good, right? So you have something to relate against. So let's say, for example, the previous version of the model would have a shorter tour, then this would mean that the current solution is not that good, and we will make it less likely that we will see that again. And you can just repeat that, let's say not 10 or 20 times, but like 1 million times. And then what you get is a model that's actually quite capable of generating these solutions. I will show you also a bit of that in a second. So now you may question, what is then actually the type of neural network model that is underlying that? And I won't go into details, but basically it's based on graph convolutions and this attention is all you need paper, which is like nowadays all the models, I would say, like ChatGPT, but also like state-of-the-art models in vision, they are all powered by transformers, and transformers are basically proposed in this paper. This is a special type of neural network architecture, which is quite general, very powerful, I would say, and that's what we actually used to solve this problem as well. And so we use that because the whole point, of course, of using machine learning to solve an optimization problem is that it's more flexible, let's say. If we have a new type of optimization problem, the sort of promise is that we don't need to think about how to solve it, right? We ideally would just give it to our machine learning model, to our black box, and it would come up with a solution or like an algorithm to be able to solve it. So in order for that to work, it must be flexible. It must be able to solve different types of problem, right? If we're just going to solve TSP and spend a lot of time on like how do we model it as a machine learning problem, I may just as well spend that time to just solve TSP instead of like, let's say, the machine learning problem. So we did a lot of experiments for different variants of problems. So we did the TSP problem, but we also did like a variant which is like the orienteering problem. So there, let's say you don't need to visit all the locations like in the TSP, but there's a certain price if you visit a location, and you just have like a maximum total length of your tour. So that's like a variant of the problem. We also did like a price collecting TSP, which is sort of inverse problem, like you want to at least visit a number of locations, let's say, but you want to minimize the length for that. And we did my favorite problem, the vehicle routing problem. I think one of the first papers there was another paper at this time actually that also considered this problem. And what we show is that we can basically train the same model architecture. We can train the same model for each problem, and we can just use the same hyperparameter. So you only need to make, let's say, the absolutely necessary changes to accommodate for the constraints, right? To make sure you get the feasible solution, to make sure you use the right objective function for the different problem variants. But then for all of these problems, you could pretty much apply the same methodology. And I think this is what also encouraged like a lot of people to try this for a lot of other problems as well. Now, then if we look at the results, here we have a visualization, which is also on the GitHub, where you really see the model in action. So you see how it like one by one constructs a solution, and this gray bar that you see pop up, that's actually a probability distribution, where you see that it's actually very confident. Like in most cases, it just predicts one bar, so it predicts like 99.9%. It should go to this next location, and very occasionally it's like actually considering two different positions. And I think this is a property of neural networks, especially if you train them with like reinforced this algorithm that I've shown. Then if you train for longer and longer, a model will just get more and more confident and convert to being very confident in its predictions, and that's what you see here. And you really see how this is able to, let's say, in a single pass, construct a solution. Now, of course, we will go into that. This is not the optimal solution, right? It's very hard to like just construct, let's say, in one go the optimal solution. But I think in terms of a constructive algorithm, I think this is really impressive. I would want to challenge it. Maybe I should have made that the lab, like try to implement a construction heuristic for TSP. I think it's really hard to do as well as this model is able to do. Like for example, we have like the nearest neighbor strategy, which says just go to the nearest neighbor. But then if you skip over some nodes, you run into problems in the end. And so this is really able to do much better. And maybe you could also try once to just like draw a tour by hand. I'm pretty convinced that it's pretty difficult to get the same quality solution. So in that sense, it got superhuman performance on the first try, we could say. But then also for the vehicle routing problem, we got quite nice results. Like optically, these tours look quite well, and they are within a few percent of optimality, which I think for a constructive approach is rather nice result. So to summarize that, what we really see when we use this model for the different types of problems, that, you know, when people, let's say 30 years ago, started working on these problems, they came up with some heuristics, and we can see that if we learn, let's say, this heuristic using this neural network, we actually get better heuristics than, you know, would be hand designed if you think about it. It also improved over some previous attempts. But of course, it's not, and this is not what I want to claim, a practical method or like state-of-the-art method for solving these type of problems, right? If you do advanced techniques or you do like search, for example, if you start with a solution but you improve it, then naturally you can get much better solutions than if you construct them in a single go. So it's more, the point of the paper was to show like, hey, this is what is possible, and I think it's quite impressive what it can do, but it's not meant as, you know, you should now just go and apply this to your problem because it will solve your problem, right? It was really intended of like, showing, yeah, in this direction and capability of neural networks. And then I think it requires more creativity to really get to state-of-the-art performance. But nevertheless, we got to, let's say, within a few percent, depending on whether you just do one construction, or you could, of course, also sample multiple solutions and just take the best solution. If you do that, then you get much better solutions quite quickly. Okay, so now I would like to go into a bit more, let's say, of conceptual analysis, you could say, of, well, not only this method, but these type of approaches. So I made the comparison, let's say that's what I started with, of let's say predicting solutions to, let's say, predicting translations, right? A machine translation setting. So if we would have a machine translation problem, we can say we have some sentence, right? We put it into a neural network, and what we get is a translation. And with that analogy, when we do like what now sometimes is referred to as like neural combinatorial optimization, then we take a problem, right? We insert it into a neural network, and what we get out is a solution, right? So this is just predicting the solution to your problem. And from maybe the perspective of sequence modeling, this makes a lot of sense, right? You can use the same model, you can use the same optimization techniques. Pretty much it's all the same, you could say. But there is a very important difference, because machine translation, as an example problem, it is different from combinatorial optimization as a problem. And so to explain you this difference, if we look at machine translation, for example, then the major problem is how do you, let's say, score a translation? So given that I have a translation for a certain sentence, is this a good translation or not? And this is really a learning problem, right? This is where you want to learn a model which can sort of, given your data, predict like what is a good translation, or what recognize a good translation when you see it. And there, on top of that, there is the challenge of then actually finding a good translation. So let's say I would have a model which can say, okay, if you give me a translation, I can tell you whether it's good or not. Then still I need some methodology, right, to actually find then which translation from like the huge search space of possible translations. So that's like the inference problem. And then that is a computational problem, you could say. Whereas if we, on the other hand, look at combinatorial optimization, then, you know, scoring a solution, if I give you a solution to a route optimization problem, that's trivial, right? I can just compute the objective. That's actually not a learning problem. And it's purely, let's say, so we could say that's like not a problem, actually. It's purely about finding a good solution from the search space, and that is the computational problem. And so maybe that's a bit abstract at this point, but it's really about, do you sort of know your objective function, and is it just like learning to find, you know, an element in your search space? That's what we do with optimization, whereas with most machine learning type of problems, actually, we're also trying to sort of understand from data, like what should the solution look like. And with that, it means that if we would have like a machine translation setting, then we care about the quality, right? And the computation is actually a second concern. That's why we are seeing now these bigger and bigger models, which can just give like very good like language generation. Whereas in combinatorial optimization, it's always about, we want to minimize the cost, or we want to minimize our objective function, but at the same time, we want to use minimum computation to do so. This is because if we have like infinite computation, right, we can just try all possible solutions and our problem is solved. Whereas if we have a machine translation problem, even if we have infinite computation, it's not trivial to write like a simple computer program that can translate some sentence. So this is actually visualized in this graph. So if you have a machine translation problem, then if you use more computation, actually it doesn't always mean that you get better quality solution, right? You also need more data, you maybe need a different structure of your architecture, whereas in optimization problem, it's really trivial. If you just spend more computation, you can just do more search, you can just do more tries, And you really need to mess up if you want to get like a worse quality solution. It's pretty trivial to leverage more computation. And so it means for optimization, if you if you have like infinite computation, let's say, then with any algorithm you could argue, even like if you do random search, if you just do exhaustive search, you will eventually get to the optimal solution. And that means that it's actually trivial, the problem, if you have enough compute, right? So the goal is always, and this I really want to stress, right? It's not about finding better solutions. It's always about finding better solutions within a limited amount of time, or it's always about this trade-off of like how much time do I spend to find a solution. And then using neural approaches, let's say, using neural networks to improve your optimization algorithm, it's always about, let's say, pushing this curve to the lower left. And with that, I would want to encourage you all, like if you write a paper on this topic, like give a curve, give a trade-off, and make clear like how does time, let's say, versus cost influence, because you need both dimensions in order to be able to evaluate really whether an algorithm is an improvement. Now, if you want to push this curve down, right, and if you want to do that by using, let's say, neural networks inside your optimization algorithm, then one very common approach, or very sensible approach, I think, is to use neural networks to make better, let's say, decisions inside your algorithm, right? So we can think of like a branch and bound algorithm where you like use your neural network to make the branching decisions for you. And that means actually, if you use neural networks inside your algorithm, you're adding a lot of computation, right? Because neural networks, they are like big models, they require a lot of computation actually to use. So that adds actually to the computation, and you're doing that with the goal of actually making better decisions in your algorithm, which is with the goal of actually reducing computation, right? For example, having like a smaller branching tree to get to prove your optimality. And so this is not financial advice, but you can see this as an investment, right? I'm going to spend some computation time to ask my neural network, what should I do? With the goal that, you know, I spend less time like searching around in my search space, but we should make sure that we do this in a way that it pays off, right? And so with that, I always want to like evaluate, let's say, approaches. So I can evaluate papers, but also if you have an ideas, I think really at the start of like starting a project, you should do this analysis. Like you should think about, let's say, how much computation do I need, let's say, to use a neural network to make some decision maybe in my algorithm, and what will be the impact of that? And on this axis, I can say like question for the audience, where do you want to be? Top left. Now it's the speakers answering, that's a pity, but otherwise it's correct. Thanks. Yes, definitely you want to be on the top left, right? So you want to make sure that you don't spend too much computation, but you get like high value from your neural network decisions. And with that, I have to admit that maybe the approach, you know, I took a few years ago, like starting my PhD, of predicting solutions directly, it's questionable whether that's like the way to go, because you need to make a prediction in every step of the process, right? And it's quite computationally costly, whereas, you know, you don't get an optimal solution, or you don't get like mind-blowing quality, you could say. So it's not in this top left, I think. And you know, you can get better solutions by doing more samples, right? But it doesn't bring you closer to the top left position, because you get like better results, but you also take more computation. So it's a bit of a question whether that's better. And I think, for example, if we're talking about like, I think there's like many people looking into like learning to local search, or to use like some neural network inside a local search algorithm. Very often that means you need to make predictions over and over again, right? For every step, or for every local search step I want to make, I need to make a prediction. And this can add like really a lot of overhead. So even if it works really well, if we get like high value from it, it also takes a lot of computation. And with that, I was just talking this morning to Elias, because we had a discussion on it, but I think like in a branch and bound algorithm, for example, is a very sensible approach. Like you need to make your predictions maybe like when do you want to branch, but then a lot of it's not like the bottleneck, let's say, for the overall algorithm, because a lot of computation is also in like solving for the node, right? The relaxations and doing heuristics and whatever. So whereas it's actually quite high impact. If you make the right branching decisions, right, this is known, this can have a really high influence on like the size of your branching tree overall, runtime of your algorithm. So with that, I would encourage you always think, if you want to start a project, on, you know, what components maybe of my maybe classic algorithm, which doesn't use machine learning, do really have like a high impact on, let's say, the overall evolvement of the search trajectory, you could say. So which components are likely to have a large influence on like the result you get, but also do not require like either hugely complex model, maybe they are like simple decisions, or are not like too frequent, let's say, in how often do I need to make this decision inside the algorithm. Because if you need to make very frequently decisions which are like very difficult, which require a big neural network, you just add so much overhead that probably it won't pay off. And I think this is what is also seen in quite a lot of papers. And then probably there's also something in the lower right. Fortunately, I don't have any examples, which means that people haven't tried this, which I think is a good thing. Okay, yeah. And okay, maybe it's like selection bias, yes. Well, then that's a good thing. I'm sorry for if you have papers, you know that happens, but it helps you to encourage you to move to the top left. And so the way to remember this is, I would say, count your flops and make them count, right? Where flops is like the number of operations your neural network uses. So really make sure it's worth using a neural network to make your prediction. And now a very nice example, right, of this, I think, is AlphaGo. So people have tried to solve the problem of Go for decades, I think, right? People have used tree search. Like, I'm assuming, who of you knows about AlphaGo? Okay, yeah, I was thinking like I should ask the positive question, otherwise I don't know if you don't respond. Okay, so that's great, so I don't need to explain this. But anyway, people have tried to solve Go, right, using tree search, using look-ahead search for like decades. And so people have also developed heuristics, right? Like how do we score board positions, like what are good moves? And then at a certain point, DeepMind came with this algorithm, which was really able to blow away the competition, actually beat the world champion by using a neural network to, you know, make two predictions, actually predict like which moves would be promising, so you can use that to sort of prune your search space in terms of what should I explore, but also if you like do search up to a certain level of depth, can you score a certain board position, like how promising is it for me? And they used neural networks to do that, which adds actually some overhead, right? I think it's quite a big neural network, quite expensive, but by doing so, they were able to get much better results with a much smaller tree search, right? This really outperforms classic tree search, I think, by a huge margin. So it shows, and actually that was the motivation for me, maybe even to start a PhD, that it's possible, that if you do it in the right way, if you find, let's say, the right decisions to parameterize the right neural network and you train it well, it's actually possible to even add like a lot of overhead using a neural network, but reduce, let's say, the search tree by so much that it pays off in the end against an alternative algorithm. And so with the other example, I already mentioned it quickly, if you do like learning to branch, for example, then you can use a neural network to make your branch predictions. And I think this is quite a nice example. And so one thing I would like to propose is in my nowadays favorite algorithm, which is hybrid genetic search. This is what we used for the challenges that Tias mentioned, which is like a genetic algorithm combined with a local search. And there, this is actually what the lab will be about. I think it's a very interesting idea to see if you can learn, for example, to select which parents you would combine in a genetic algorithm. Currently, it's pretty much random, which for me means that it's quite likely that you can improve it, although also random tends to be quite a strong baseline in some cases, but it means that, well, there is at least some opportunity to apply learning, let's say. And I think it's quite interesting because, you know, the parent selection inside this algorithm, I will go into more details later, it's not done very often. Like most of the time is actually spent in like combining the solutions, then doing local search. So if you can spend some time to make like a very good good selection of like which solutions do you combine in your algorithm, then that can have quite some influence, but you don't need to make these decisions too often. So I think in my trade-off, this is quite a promising idea, and I just want to like have you all try this. So that's what the lab will be about today. Okay, happy smiling face. Anyway, so I think in the end, what we should do is actually combine the best of both worlds, let's say. So we have a lot of algorithms, we have a lot of knowledge, there's a lot of structure of problems that we know. We can exploit this, right? But then very often inside our algorithms, there's a lot of choices which are either like sort of randomly determined by the person who implemented the algorithm, or it's like, well, just quite arbitrary. And I think that's where we can apply machine learning and see if we can improve that. And by doing that, we can really have the best of both worlds, you could say. And one side note I want to put in here is, so I'm really talking, if we're talking about like machine learning for optimization problems, about like how can we use machine learning actually for, let's say, learning how to optimize. So inside the optimizer, and of course, if you think about machine learning and optimization, how they interact, there's also like a huge opportunity, I think, in using machine learning for learning what you actually want to optimize, right? So we get into like the predict and optimize setting, which we have seen yesterday quite a lot. And I think that is just as promising, or maybe even more like the natural approach to use machine learning for optimization problems. But today will really be about how can you use like machine learning inside your optimization algorithm. Okay, so I already talked for quite a bit, I think, about like this traveling scientist problem, or TSP. I want to take you a bit with me on a tour, like through one other project I did, and to this algorithm that we used for these challenges, which will then lead us to also the lab exercise for today. So, quick recap, right? We already saw the TSP problem. I explained it to you. I should get this animation of that, and we saw some results for that. Now, sorry, I thought I had one recap slide, but I see I have another one. Anyway, I'm going to skip here to the next part. So, in the context of this trade-off, let's say this method I proposed, like predicting solutions directly, I think it's not the way to go, let's say, long-term. So I'm very happy if people cite my paper. Please keep doing that. But I wouldn't recommend you to just go on and take this architecture and to just apply it to a new problem. I think we need more creativity to sort of combine or use these neural networks in different type of ways to solve our optimization problems. And I think there's also a very nice blog post that actually Chaitanya Joshi wrote about like some recent advantages in this field of like deep learning for routing problems. And in the next part, I want to talk about the project I did, which actually follows up on a paper also he wrote, where he proposed to also consider this TSP problem, right? But take the input as a graph, but then rather than, let's say, doing this autoregressive approach of predicting a solution one step at a time, right? We can just take like a graph neural network, we can take a dense neural network and just make predictions for all edges in the graph at once, right? So we can say, can we predict for each edge what is the probability that this will be part of the optimal solution? Not sure if that's correct, because that's not a probability, but can we sort of predict whether the neural network thinks it should be or it's part of the optimal solution? And then what you can do is you can train that, you know, just using supervised learning. You just give it example optimal solutions for example instances. Then for a new instance, you can just use your neural network. you can make a prediction, and you get something like a heat map, we call, which says like, hey, these are edges which are very promising, let's say, very likely to be part of the optimal solution. And then what they proposed is to use a simple beam search on top of this. So you just start from a point and you just go over these edges and try to construct a solution out of that. And I think that's promising because it means you only need to run your neural network once at the start, right? So the computation is sort of manageable, and then you can just construct your solution. And so the nice thing is that this was actually more efficient, let's say computationally, and it got better results than the method I shown you before. So this got me quite excited, and I think the reason it got better results was just because the model was bigger. It was trained, I think, using more data with supervised learning, so it could really do better predictions actually with, you could argue, less expressive model, because it needed to predict all these edges at the same time. But I think this beam search step, it's not the best way actually to go from this heat map to a TSP tour. And so with that, we proposed actually to combine this approach, use the same model, but use it inside a dynamic programming algorithm. And this is what we called deep policy dynamic programming. And you know, if you want to have the short summary, or if you've already seen it, so it's a framework we proposed for vehicle routing problem, which restricts actually the dynamic programming state space to the most promising parts, and it does so by using this heat map of edges predicted using a neural network. And so to explain you a bit on how that works, we need to look at, let's say, the classic dynamic programming formulation for the TSP problem. And so that works as follows. So let's say we can break up the problem, right, of forming an optimal tour into smaller sub-problems, right? So we can say if for a given set of nodes and a given current nodes or location where we are, we can, if we know the optimal tour, then we can express this actually recursively in terms of the solution to smaller sub-problems. So you can say the minimum cost to go, let's say, from the starting node, from 0 to the node I, visiting all nodes in a certain set, right? It's the minimum over all possible, let's say, previous locations I could come from, and then like the shortest tour, which would then visit, maybe I should use the pointer here, which would then visit like all of the remaining nodes and end at the previous node, and then add the distance to go to the next node. Okay, maybe it's not the best explanation this way, but visually you can depict this as saying, let's say I want to visit these 4 nodes, starting at 0 and ending at 3. Then there's basically 2 options. Because before we could arrive from this node or we could arrive from that node, and then what you can show is that, you know, this partial solution, let's say, it's worse than this partial solution, whereas any completion I could make to this solution, I could also use it to complete this solution. So this can never be part of an optimal solution. Is that somewhat clear? But basically, that explains the dynamic programming principle. So you can say for certain partial solutions, you can just rule them out because you can show that there are partial solutions which just are always guaranteed to be better. So we can say we can dominate them, and that means that we can remove them actually from our search space. And so with that, we can sort of relate the dynamic programming approach to the brute force approach. So brute force would be, just going to try all possible options, right? So where do I go first? Where do I go next? You get like n factorial different solutions. Whereas with the dynamic programming approach, you have like a smaller state space, which is exponential. And typically, in terms of these formulas, it's sort of expressed backwards, but you can actually quite nicely just align this program. So you can view actually a dynamic program as just doing brute force. But let's say in every step, if you would do it like in a breadth first manner, so first like every first step, then every second step, you just remove all solutions which are dominated. Then basically a dynamic program, you can interpret it as doing a brute force search where you just remove dominated partial solutions. And this view is quite nice because it allows us to make some changes to it. So the advantage is that using dynamic programming, your complexity goes down, let's say, from factorial to exponential, but that is still like impractically large for any feasible or like any reasonable problem size. But then what we can do is actually, just like you could say we can do a beam search, it's something which is quite common in machine learning. So that means I'm just first going to try, let's say, 10 next places to visit. Then for those 10, I'm going to see all possible next stops, and then I take the 10 best again. So this is a beam search, which basically means you're going to do sort of a brute force search, but you're just going to limit the number of options you're going to consider. You can do the same thing in this dynamic programming, where you just limit the number of solutions you consider at the same time. And then we get into what we call restricted dynamic programming. And the nice thing is this complexity will be linear, because you can just determine, let's say, how big your search will be. But of course, you need to somehow, let's say, decide which solutions you're going to keep in your search. And for this, you need a good policy, basically. And in classic dynamic programming, let's say for vehicle routing, people have said, let's just use the cost of the solution up to now. But this means you will get very much a bias towards like first visiting like the cheap edges, for example. So that's not a good policy. And then what we actually propose is to use our neural network to do this. And so then what you get as algorithm is basically you just start with an empty solution. You're just gonna expand the solution, which means you're gonna look at all possible locations which you can visit next. So you get a set of possible like partial solutions. Then you're gonna remove the ones which are dominated. So the ones where you can prove like they will never be part of an optimal solution, because there's one other solution in your set of solutions that is always better. And then we're just gonna restrict to keep at most B solutions, and so for that we use the policy, and we can repeat that until we have like a complete solution. And then the question is, how do we define the policy? And for this, we use actually this heat map value, so this scores, you could say, for the individual edges, and we can just add them up. So if we have a partial solution, let's say, in this case you see it, you can just add up, let's say, all the values of those edges, and that will give an indication of whether this partial solution is a good solution. Now, of course, in this situation, this is not a good partial solution, right? Because you would sort of skip over some nodes which are relevant, and so we take that into account as well. And we do that by saying like, hey, if you're going to have this partial solution, then some edges will become unusable because of that. And you sort of take that into account in the score of a solution as well. So here's a bit of engineering, or like the creativity, I would say, of like how can you actually translate, let's say, this heat map values, which I think contain very valuable information, to make a prediction for a complete partial solution on how promising is this to solve your problem. And so that way, we have a way to score actually for a partial solution, how good is it, right? And that's very useful in a constructive approach if we can make selection. Yes, continue. Good.
For the start function, here you combine two measures, but how do you balance the importance of both measures?
You mean like the heat and the potential? I think here the weight is just one, which is sort of justified by the unit. Like basically for each node, you have some value between 0 and 1, like how good is the edge that is in there. For each node which is not visited yet, you have some value between 0 and 1, like still the candidate edges that are left over, how good are they? And so with that, I think it's justified to just have them equally weighted, right? Basically, this potential is sort of an estimate of the score you would get if you would complete the solution. So with that, they should be the same weight. Does that answer the question? Yes. Okay. And so, yeah, we can recap the algorithm, but basically it means that we can start with an instance, right, which is just like a set of locations for the TSP which we want to visit. We put it into our graph neural network. We get a heat map, and this is the very powerful aspect. I think you only need to do that once. So you just run your neural network. you get your predictions, and then you can use that inside a search algorithm, which for this reason can be very efficient because it doesn't need to consult a neural network anymore. And you can do it like a much larger scale search, but really focused on, let's say, the search region, which was defined by the neural network. And so we did, yes? No. Yes, that's correct. So you never predict zero, right? Because it's like, and so all the edges have some non-zero score, and basically the map is still fully connected. We did something where we do like a hard threshold, but then indeed you risk that you cannot find a solution. But you can always use it to score the best ones, let's say. Yes. And so we did experiments for the traveling salesman problem, traveling scientist problem, I tend to call it, vehicle routing problem, but also TSP with time windows, which I think is quite interesting because this is a much more constrained problem, right? If you have time windows, which means you need to visit within a certain time frame, a certain customer, then the geographical aspect becomes much less relevant actually, and becomes more of a scheduling problem, like when do I visit, or like in which, well, the order is much more determined actually by the time windows as well, but the search space is also much smaller or much more restricted, and dynamic programming approach is really powerful for this. So you can imagine you can construct a solution in starting or in chronological order, let's say, and then it's much easier to satisfy time windows than if you would do like a local search. If you would swap things, then a lot of things would shift. It's really hard to manage time windows. And so I think this dynamic programming approach is really powerful also for like more restricted problems actually, because the search space is smaller by itself then already, which is good for a dynamic programming algorithm and challenging, I think, for a search algorithm, because it needs to like jump to infeasible parts of the space. And we actually show, well, a number of results. I'm not going to go into details, but that you can get, again, not optimal results, but I think quite nice results. And especially if you, let's say, compare them to, that's in the next slide, I would say, if you compare them to classic dynamic programming algorithms where you don't use like machine learning, but you would just use, let's say, the cost as a way to score partial solutions. This is what people have done in like routing community, and you get like gaps up to 10%, 10, 20%, let's say. It's really not working well, and we can really cut that down to like within 1%, for example, by using this neural network to score the solutions. And the previous slide, I skipped over it quickly. It shows, if you compare it to LKH, for example, which by now I think is not the strongest baseline anymore. That's the hybrid genetic search. So that's what we put here as 0. So that would be the best state of the art, but you can get to like within 1%, right? And I think being like a flexible and general method comparison to LKH is somewhat fair. It's difficult to compare. We use GPUs. How do you compare against the CPU-based method? But at least we did some comparison, let's say, of the trade-off of time that you spend and the quality of the solution you get. And you can see that, well, for this blue lines, which is our dynamic programming approach, you can get somewhat, I think, in the reason of this like quite heavily engineered heuristics, I would say, with, I think, quite interesting, very different approach, which is based on like dynamic programming, which is in principle an exact method, but just made into a heuristic by restricting the search space. Okay, so that summarizes DPDP. It's a framework for many VRP variants, I would say, and you can, well, have all nice sorts of properties. So you can trade off actually the compute and the performance by just increasing the size of your search space, let's say. And I think this is really powerful, or I would want to encourage people to think also more in this way, because it doesn't actually use reinforcement learning. It uses like supervised learning. It just learns from example solutions, and you know, if you have example solutions, use them. That would be my advice. If you have the possibility to generate like solutions, even if it's by investing a lot of compute, you only need to do that once, right? And you can just use your training set multiple times. And with reinforcement learning, right, it's always like online. You have to include maybe your solver in the loop. That's just very expensive to train. And then if you change some parameters, you have to do it all over again. Whereas if you can do something where you can, you know, disentangle, let's say, the data generation process from the learning process, then this is really powerful. This is what AlphaGo does as well. Like, it just plays some games against itself, and it gathers all the historic games and uses it for training. And I think with this, you can do much more iterations of training. You can try much more settings. I think that's a really powerful technique that we should, yeah. Consider. Yes. But so for routing, I think there's not very often, there's multiple optimal solutions. Of course, you use heuristic. So I think for some problems, I also even didn't use optimal solution, but just very good ones. So you can have multiple solutions. But I think it's like, I think you have yesterday as well, like the averaging is over the batch dimension. So for one instance, you have one optimal solution, but you have like a million different instances, and then it's fine indeed. Because you're very true, like a small change in the parameters, right, could completely change the optimal solution. So in that sense, it's very noisy label, you could say. But yeah. Yes. Exactly. Yeah. Yeah, but that contains the same edges, right? So yeah, it's a bit on whether you consider directed edges or undirected edges. So for like the sequential model, there's like a lot of symmetries. You could say like any or like if you take a different starting position, you have the same solution. And I think this is what this POMO, like policy optimization, multiple optima, did. They exploited this symmetry basically. But if you predict edges and you consider undirected edges, it's all the same. Any other questions before I go on to the next part? Yes.
Have you also considered looking at close optimal solutions, so extending from pure optimal to within 1 or 2% of optimal?
Yes, so I think for one of the problems we were not able, like for VRP maybe, or at least we didn't use like a solver that proved optimality. So you can just use heuristics as well, and as long as it gives you good selection of edges and the network will generalize from that, that will be fine. But I think, yeah, the better your labels, the easier it is to learn for your neural network, yeah.
Could it be that if you, because every instance has only one solution, could it be that if you have multiple per instance, it somehow can generalize to more robust solutions? Or you don't think that?
No, because you train for, because you train for multiple instances anyway, right? And you can never predict exactly this one solution. That's very difficult for the network, unless it's actually overfitting. Of course, you want to avoid that, but if you regularize it well that it doesn't overfit, then somehow it has to say like, hey, here I can't predict exactly the optimal solution because this other one could also be likely, and it needs to interpolate, right? Because it's like constrained by the other data points to make consistent predictions across all instances. So I would say you have that effect. It doesn't matter if you have like multiple labels, let's say, for the same data point. Yes. So it depends a bit on the problem. Like for the TSP, I think we had optimal solution. Then for the VRP, we didn't have proven optimal solutions, just very good ones. Yes, exactly. Yes. Exactly. Yes. Didn't scale them. So that's something. Scaling is definitely a challenge. So the neural network, it can scale like conceptually, no problem, right? You can just input a bigger instance, it will make predictions. But of course, quality of the predictions will degrade because it's not intended for this purpose. So in the first paper, we have some experiments on generalization, also to bigger size, and I think other people wrote very nice papers about this. But to scale like to 1,000 customers, for example, I think you would need different approaches and also sparsify a bit. Like I think it's definitely possible, but you just need to handle it differently. Okay, so now I want to say something quickly about like hybrid genetic search, which I have to manage expectations. For now, it's an algorithm which doesn't actually use any machine learning, but the lab will be about can we use any machine learning inside this algorithm. But this is what we used for the Dymax VRP with time windows challenge. So VRP is vehicle routing problem. And well, given that the lab is about this, I want to introduce this to you as well. And so the Dymax challenge, it's like a quite prestigious challenge, I think, which has been organized for like a few decades already. Like every few years there's a challenge, and like in 2021 this challenge was about route optimization problems, and there were multiple tracks, but we participated in the VRP with time window tracks, which is basically a vehicle routing problem. So you have to make a set of routes. Every route has like a limited capacity of the customers it can include, and every customer must be delivered within a certain time window. So you have to make sure you're in time at your customers. And in this variant, the objective was to minimize only the distance. Like sometimes it's also an objective to minimize the number of vehicles that you used. Here it was distance only. And the algorithm that we used, and I shouldn't take too much credit for this because this was all like originally developed by Thibaut Vidal, who was actually also one of the organizers of the challenge, but it's hybrid genetic search. This is basically state of the art for vehicle routing problems, and it's a genetic algorithm which is hybrid because it uses a local search, let's say, in every step. And so the way this works is we have a population, which is sometimes called like a pool of solutions. Who doesn't like a pool, especially on these days, maybe yesterday? And what we do is we initialize the pool with the number of initial solutions. And very importantly, we don't only consider like feasible solutions, we just relax, let's say, the time window constraints. So we allow time windows to be violated, which means we have also infeasible solutions. So we have a population or a pool with, let's say, 100 different solutions, which contains feasible and infeasible solutions. And then this is an iterative algorithm. So in every iteration, we take actually 4 solutions from the pool. Can be feasible or infeasible. And this is not so nice. We're going to apply a binary tournament. So you can maybe replace this during the lab, but what the binary tournament actually is that we want to trade off, let's say, the quality of the solution, but we also want some diversity in the solutions that we consider. So these solutions are basically going to fight. The one says like, I'm the best quality solution. The other one says like, I'm more diverse, right? And based on, let's say, some weighted score of this, we pick one of the two. So this means we just get 2 random solutions from our population, but we pick the best one, taking into account quality and diversity. And then we do that 2 times, and we're going to combine these solutions. So it can be 2 infeasible solutions, can be feasible and 1 infeasible, or it can even be 2 infeasible solutions. And they're going to do what I call the dance of romance. And then what we get is baby solutions, right? This is a very realistic algorithm, I would say. So we have these solutions, we combine them, and we get what we call an offspring solution. And now this is very helpless little crying solution, you could say, because the way we combine the solution, it doesn't look nice. You take some routes from one parent, some routes from another, and then you have some leftovers which you need to fix, right? And that's why we need to educate it. We need to grow it into like a full-grown, locally optimal solution. So we use a local search algorithm for that to improve it until like the new offspring solution is locally optimal again, and then we're going to insert it back into the pool. we always need to wait for that a bit, but there it was, right? But this solution doesn't have to be feasible, right? Because our local search, this is like the power of the local search, it allows for infeasibilities as well. And this is sort of like it smooths out the problem. It makes it easier to go through the search space because you can like sort of cross the infeasible region as well. But of course, in the end, you want feasible solutions. So what we do is like 50% of the time, we toss a coin. We repair the solution, which just means we rerun the local search, but we increase the penalty for like violations of the constraints. And then, well, sometimes, very often, we get the feasible solution. If we do that, we can insert that back into the pool as well. And then we repeat this for a number of steps. We get like very many solutions in our pool, right? Which means very harsh algorithm. We need to just remove some people from the pool. Some solutions. So we're going to pick the best solutions, let's say in terms of quality, but also diversity. It's really important in this algorithm. You know, this pool basically sort of covers your search space with a number of locally optimal solutions. You don't want them to be all from the same region. So there's like a diversity criterion in there, and you take into account both the quality and the diversity of the solutions. And with that, you know, in every generation, we say we remove a number of solutions from this this pool, and then basically we can repeat that process. So now the question, so this was the, let's say, existing hybrid genetic search algorithm. Thibaut had a very nice implementation of this for the capacitated vehicle routing problem, so no time windows. And what we did was basically built on this. So we added a number of initial heuristics for initial constructions. We actually improved, let's say, the crossover mechanism, so the way to combine solutions, and we added support actually for this time windows to support like vehicle routing problem with time windows. And then we improved like a lot of things in the local search. So we added another operator. We made sure that we could like increase the neighborhood size as we as the algorithm went, and we did a lot of optimizations to make it fast. And this was really powerful in the end, because after running it for some time, we really found new best known solutions, let's say, for this this problem. I think I'm going to skip a bit over the details of like how do you support time windows in this problem, because I think it's not so relevant for today. But if you're interested, there's also very nice papers, and you can talk to me. But as this, there's a very elegant, let's say, data structure in this algorithm, which can make it really fast and efficient to evaluate also local search operators involving time windows. But for this this combination, let's say, of offspring, so of combining solutions from two parent solutions, there we use a selective route exchange, which means we have two solutions, right? We see them here, and we take some routes from the one solution, we take some routes from the other solution, and then we can sort of, like, depending, well, for both solutions, we sort of divide the all set of routes in two, and based on how we combine them, we can get like two different offspring solution. And this method is called Shreks. So basically you have Shrek, and then you have Fiona. Okay, the first time I did it, I found this a nice joke, and now I'm like, okay. But anyway, you get baby baby ogres, right? And then these are your offspring solution. And so we added that on top of like the original solution, or the originally implemented crossover mechanism was quite simple. It just took some part of the solution, then it just completed that with all the orders, let's say, in the order of the second solution. But I think this this route exchange, that is what is currently implemented in the library that we have. I will explain that later, PyVRP. And so this is also what you can base on today. And then, of course, it's a very natural question to ask, like, which combination of parents, right, would make for a very good offspring solution if you would combine them. And currently the selection is really random. Like, you just get two parents, or I think there's maybe very small heuristic in there, like they shouldn't be the same and they shouldn't be like completely different. But I think there's a lot of room for improvement. Like, can you somehow predict, if I take this combination of parents, sort of, do they have complementary properties maybe that can recombine nicely, especially if we would then improve the solution using local search. And so in this algorithm there is a local search, which is really like it does all the standard operators. It does, like, for example, like swapping two nodes or relocating some nodes or like recombining parts of routes. And all these operators are defined, let's say, in terms of a neighborhood. So we don't consider all possible moves, but for each node, we only consider moves with like some nodes which are like in the neighborhood. And then we do a lot of like efficient tricks, you could say, to make sure that we only evaluate a move if we think it is promising, or some cases you can bound them quite early on, like, hey, you don't need to try this. And one other thing that was in here, what really made it powerful, is the swap star operator. So this is a special operator which exchanges actually two nodes between two routes, but then it doesn't just swap them, but in the other route it inserts it into the optimal position. And if you implement this nicely, you can do some caching on like how should you insert certain nodes. You can implement this very efficiently, and you get like quite a large neighborhood that you can search quite efficiently. And that is actually exact for the normal vehicle routing problem, but if you have time windows, then you can no longer evaluate it exactly efficiently, because that's just too computationally intensive. But we just do an approximation that works quite well. And then additionally, what we do is what we did, at least for this challenge, I think in the current version, we simplified it in the open source version, but we increased the size of the neighborhood and the population, right? So first, you want to get quickly good results. So maybe you just want to do a simple search, but then if you start to converge, you want to enlarge your neighborhood and to enlarge the population to sort of intensify your search. And so we did this for the Dimex challenge, and there were some like reference solutions, we call them now. So they were like the previous best known solutions for this variant, and we got to like 0.004%, let's say, with a running time of like 1 or 2 hours, depending on the size of the problem instance. And this was, really enough, let's say, to win the challenge. So this is why I'm quite excited about this algorithm. I think it's extremely powerful. It also proved to work well in this competition, but I think it makes a lot of sense to me. Like, you have a solution space, right? You try to cover it somewhat, like with a lot of solutions. So it's like you want to find the minimum for some service, and I just throw out a lot of marbles, let's say, which all go into like the local their local optimum, and then you can like recombine them to get like new locally optimal solutions. And so I think having this combination of like a genetic algorithm and a population-based method, which it can cover the whole search space, but then with the local search you can get into like a local optimum, and I think that is just really powerful. And that's why I'm quite excited about this approach. But at the same time, I think there are still a lot of parts in this algorithm which are just random or quite arbitrary, and so I see a lot of promise also in using machine learning actually to improve this algorithm. And actually, for that purpose, I proposed actually a challenge around this topic. So following up on this Dimex challenge, I said like, hey, wouldn't it be nice if we can follow up on this very powerful algorithm, but encourage actually people from machine learning community, to do better. And so that was really the goal of the Euro meets NeurIPS vehicle routing competition that was organized last year, to bring together like people from operations research and machine learning, and then solve, let's say, this vehicle routing problem with time windows. Then I had some co-organizers who said, like, if we're going to do machine learning, we should add some aspect that makes it more interesting for machine learning people than purely combinatorial optimization problems. So with that, we also introduced a dynamic problem variant where you also had to sort of deal with uncertainty about orders that will arrive in the future. So in the end, we had like 2 problem variants that needed to be solved by the participants. And so to make that more realistic, we actually added real data from a customer from Ortec. And so we had the static variant, but also this dynamic variant, which needed to anticipate, right? And yeah, we will get to some of the results quickly, but actually the winning methods, especially for the dynamic variant, they use machine learning. Actually, one of the methods that Elias also showed yesterday. I think quite advanced methods, and really people from operations research try to do like heuristics or like sampling-based approaches, even some stochastic programming, but really machine learning approaches outperformed actually, or won at least for this variant. So I think that's quite nice to see. And so a bit of the motivation why I wanted to, let's say, also bring together this machine learning operations research, it's because I tend to see that, you know, people in operations research realize a lot like, hey, we need to use machine learning as well. There's a lot of promise, but then very often the techniques used are relatively simple, right? We use maybe feature-based methods or like random forest on some like engineered features, but it leaves, I think, a lot of deep learning potential on the table. On the other hand, in machine learning community in the past few years, like a lot of papers have come out doing something in machine learning for vehicle routing problems, but they tend to sometimes disregard also like state of the art from the operations research community. There have been many papers which made huge claims which are just simply false, let's say. And I think there's really benefit to bringing, let's say, these communities together, experts from both sides. And so for that, we had this challenge, which was very nice. Like it started at the Euro conference, it finished at the NeurIPS conference. And so I already mentioned what we did. And especially also we provided, let's say, our hybrid genetic search implementation as an open source, as the baseline. So really set a high bar, like, hey, let's start from a state-of-the-art method, also to show people in machine learning, like, hey, there are really powerful, let's say, more classical techniques, and we should actually leverage that, right? We should not try to come up with something else completely different and, you know, not be able to compete with that, but really see, like, how can we build on that. Additionally, I really wanted to encourage like some active engagement. So we had like a real-time leaderboard. So people could submit over a few months' time their solution, and they could in real time see like their rank, let's say, on the validation set. And this really encouraged a lot of people to participate also early. And you see like how this ranks shifted over the time. In the end, we had 150 teams registered with 50 final submissions, or 50 teams. 800 submissions in total over this period. And like the first team was team from the Technical University of Munich. They did something like with this differential young losses, I think, which you saw yesterday, where they really trained like end-to-end a model that could, let's say, predict not which orders should be delivered, but predict a certain value for orders, which could then be included in the route optimization, and this was trained end-to-end. I think this is all very nice, and well, they actually showed that you could win the competition with this. And people from second team also did a great job, and I'm working with them actually to open source what came out of that as part of this PyVRP library. So the goal with PyVRP is that I actually want to make it easier for people to, you know, build on the state-of-the-art in vehicle routing optimization. So, for example, this hybrid genetic search algorithm, this is the core algorithm in this library, but it's implemented in such a way that the local search, let's say, which should be very fast and efficient, it's implemented in C++, but the genetic algorithm is mostly in Python. So you can do like population management, selecting parents, crossovers, all of that is in Python, because, you know, that's not a performance bottleneck. So it's okay that that's a bit slower, but this makes it much more easy to, you know, add some machine learning model on top and experiment with that. And that is actually the lab assignment for today. And so I have to admit, I think it's a bit challenging, right? 1.5 hours is not that long, so the setup will be a bit like yesterday. Like there's a notebook which is already working, which basically shows like, hey, this is how you could use this PyVRP library to add a neural network on top of it. Now it doesn't work, so I implemented it all once. It's there, but it's very simple, right? It's very basic features, very small data setting. So it's up to you to well, first maybe look through it and understand it, then come up with some ideas like, hey, what would be needed maybe to make this this better. And so that gives just one example. I will share the link later. But of course, I see many opportunities for using learning, let's say, inside this hybrid genetic search algorithm, right? So I mentioned about like growing the neighborhood or population. You could imagine that you have like a neural network which dynamically says like, hey, at this point in the search, based on like these properties I observe, you should now grow or shrink maybe your population size or your neighborhood. You can do like parent selection, right? You can maybe learn, let's say, if you do the moves like which neighbors, so which nodes you should consider in your operators. I wouldn't recommend like going into the local search, like making like predictions in every step, right? But selecting, let's say, a search space which you then use for like a fixed number of iterations. I think those type of things can be promising. Yeah, I feel what is in there now, it's just like sort of what came out after some tuning. So I would expect there's definitely opportunity to improve that. And if you do that, that means like an improvement of the state of the art, let's say, for vehicle routing. And I think that's really where we should focus more to really achieve that. And that will also show like people in operations research like, hey, you can really like use this to actually get better algorithms than we have nowadays. And so with that, I wanted to wrap up. Thanks a lot for your time. I'm sorry for this slide. It's just in the in the slide deck, I guess. Let's keep it at a nice picture. So I think 3 minutes left. So are there any questions? Yes, please. What do you mean with when you can do this? Yeah. Yes. Yes. So I think it's. I thought you said like when you do that, but it's like fixed iteration. Every iteration you make like one offspring, and then you do the local search. But basically, you could completely redesign the strategy. So I really like to also present, let's say, this PyVRP as sort of like building block library. Like you have a local search, which means you can just take a solution, you can run it through the local search. You can say like, this is the size of the neighborhood I want these operators, just run it, and you get like locally optimal solution. And you can combine that in any way possible, right? So you can say, I'm going to run it for a few seconds, see what comes out, decide if I want to run it for longer or not. Or there's, yeah, so also with like the mutation operator, like combining parents, that's all up to you, like how or when you want to use that, basically. Any other questions? Otherwise, I think we can have a break, right?